Yeah, so the drift diffusion model is based on mathematical formulae that were actually developed during World War II by Alan Turing, and then in parallel, independently, by another mathematician called Abraham Wald for different reasons. So Wald was trying to come up with a formula to optimize quality control on arms shipments to Europe. So it would be far too time consuming and costly to check every single bomb, say, that you're sending over to Europe to fight the Nazis. But how can you determine, though, there was a big problem with a lot of dud bombs or ammunition being sent over. So how do you get the balance right between checking everything and just checking enough to know that say a given shipment should be sent back? Abraham Wald developed this what's called the Sequential Probability Ratio Test, which is basically a formula that optimizes your accuracy for a given amount of time so spent making the decision. So effectively what it meant was you would set a threshold on how much evidence again you need to determine that this shipment of arms is either okay and can be sent off, or not okay and should be sent back. Each bomb or piece of ammo that you check is a piece of evidence, right? If you check it and it's okay, that's a piece of evidence towards the send it off to Europe bound, and if you find a dud, it's a piece of evidence towards the send it back bound. But what you do is very simple. You take a running sum of all the evidence, right? So that you're adding them together, adding all the pieces of evidence together that you encounter as you go. So your evidence is going to kind of meander a bit towards the send it on bound, but then you might get a few duds and it'll meander back towards the other bound. And once it hits one of these two bounds, then that's where you stop collecting any further evidence and you send it off. And the calculation allows you to identify what a good bound would be, so that you have a certain hit rate, a certain how many false alarms are you going to end up with, how many times are you going to send back in a box that you shouldn't have, or how many times are you going to send it on when you shouldn't have. So the basic idea, though, is accumulating evidence over time, not making a decision based on any one piece of evidence, but accumulating it over time. And the drift diffusion model is basically a mathematical implementation of that test applied to cognition. So when you're making a perceptual decision, the idea is again that the brain doesn't just rely on any one piece of evidence or one little snapshot of what's going on in visual cortex. It accumulates, samples evidence repeatedly over time, allows it to accumulate up to, again, these decision bounds that would say, okay, the dots are moving left or the dots are moving right. And all that might happen very rapidly in the space of even say 100 milliseconds or a second, but it's still a progressive accumulation process. And so that's the fundamental idea, but behind the drift diffusion model. But actually there are, beyond that core ingredient of evidence accumulation, which itself took a lot of work over decades, again primarily work done in monkeys to prove that the brain actually does use this evidence accumulation process. But beyond that, there are a lot of alternative models of decision making that share that ingredient of evidence accumulation, but differ in really fundamental ways that are important for how we think about decision making. And one of them would be, for example, that question of urgency that I mentioned. So in the diffusion model, the decision bounds, once they're set for a decision, they don't move. So if you say, I need this much evidence before I'm willing to commit, that doesn't change no matter how much time has passed, even when there's a deadline. And they have other ways of accounting for how people, say, if you hit the deadline, the participant might just guess and literally flip a coin. That'd be one way of doing it. Whereas subsequent research has supported alternative models, including our own, where we studied these motor signals, showing that actually it does seem motor signals seem to move towards their threshold as time goes on, independent of how much evidence is coming in, which would be consistent with them lowering the bounds on their decisions, supporting the role of urgency. So that's one difference. And so there are alternative models that would allow for urgency, but there are a lot of other like big questions about decision making, where there's disagreement and different models that account for those effects in different ways. So just one other example would be whether or not we keep a perfect record of the evidence that we've encountered, or whether maybe information is forgotten. Like older samples of evidence might leak away or be discounted or forgotten as time goes on. That might be something that's like strategic and a good thing for the brain to do, or it might be something that just happens like because we're not able to maintain the information for long enough. So that, that brings in questions around like our ability to maintain a working memory representation of the evidence we've encountered. So they're, again, like really important questions. The diffusion model would not allow for any information to leak. It assumes that we have a perfect record of the evidence encountered. Other models do allow for leak. So this is where these are some of the examples of the kind of big questions in the field where having neural recordings can really help, because a big problem for research in this area, in human research anyway, is that you can, like, the way we test these different models is we fit the model to people's behavioral data. So we get them to do a perceptual task, and we fit the model to their data, and then see how well that model is actually able to reproduce people's behavior. Does the model perform like a real human on this type of task, or are there some differences there which would suggest that the model isn't quite right? Different models, different decision models that can differ in really fundamental ways, like I've just described, will often fit behavioral data equally well, which means we have what's called model aliasing, where, okay, we can't tell. Both models make the same predictions for behavior. We can't tell which one is right. And that's where having another way of testing the models is so important and so powerful. Having these neural recordings gives us that other way. So we can say, okay, these two models provide an equally good fit to behavior, but which of them it looks like the neural data? And often, even though they'll make the same prediction for behavior, they'll make very different predictions for the neural data. So, for example, in the case of urgency, you might find that the diffusion model and a model that has urgency in it provide very similar fits to behavior, but the diffusion model would not predict what we see in our motor signals. So that, it's a new way of testing between the models. And there's lots of other questions then where we're trying to make progress in addressing, questions around, for example, how we factor prior knowledge into our decisions. So if we have a particular expectation about what we're going to see, how does that influence the way our decisions are made? Again, there are different theories and different models for explaining that. How do we factor in the value of different outcomes? So it might be more rewarding. There might be a better reward associated with a particular outcome. And that can bias how we respond as well. Also, we're really interested currently in understanding how we evaluate our confidence in a decision, right? So we can be forced into making left and right decisions, but we also have the ability to represent in a very continuous way or graded way how confident we are that we made the right decision. And there's lots of questions there as well about how the brain allows us to do that.